Now suppose this is a container. It is in the shape of the cube. Its volume is length into width into height, mean L cube. So we can write volume of the container is L cube. Suppose it contains ideal gas, then the volume of the gas is also L cube. Now number of moles of the ideal gas, suppose small n, and the total number of molecules in the container for the ideal gas, capital N. So small n represents the number of moles and the capital N number of molecules. Now the relation is number of molecules per mole is called Avogadro's constant. So formula is number of molecules, number of moles, time Avogadro's constant. This is important relation. Now molecules are moving in the container. They are making collision with each other. Their intermolecular collisions are negligible, mean we will ignore all forces due to collisions of the molecule with each other. But we have to consider the force or the forces due to collision with the walls of container. So suppose one molecule is selected from the ideal gas, its mass m, just one molecule mass m, it has just finished collision with this wall, and now it's moving in this direction with velocity v. It has momentum. So due to momentum, when it hits here, it exerts force and there is a change of the momentum, and this collision is perfectly elastic. So this direction, speed same, but opposite direction. So the velocity is minus v, and this molecule reaches back to this point. So one molecule is traveling from one wall, it collides with the other wall, and then back to the original position, the first wall. So this is actually the distance covered by one molecule for one collision. So the question is, how much distance is covered by one molecule to make one collision? Look, L in this direction plus L in this direction. So the total distance covered by one molecule is 2L. Now the speed is same, velocity positive, negative. So according to the formula, distance is equal to speed into time. So the distance covered for one collision is 2L, speed V, and time T. So this time T is 2L over V. So this is the time taken by one molecule to complete one successive collision. So 2L over V. L one side, L other side, the total distance for one collision is covered 2L, mean just for the one trip, okay? Now, before collision, the molecule is going in this direction, which is mv, and then it's going back with a negative momentum. So here is a collision. So what is the change of the momentum? It is the final momentum minus the initial momentum. So we can write 2mv minus r positive because it's a difference. So we can write 2mv. Now, according to Newton's second law, rate of change of momentum is an unbalanced force. and this is also the definition of force. So according to this definition, force is equal to change in momentum divided by time. So the force exerted by one molecule during one collision is 2mv divided by time, 2L over V. So 2 cancelled, it becomes mv times V over L. So the force for one collision is mv square over L. This is the force exerted by one molecule during one collision. But total number of the molecules are n, and there are three axes for the motion: x-axis, y-axis, and z-axis. So three-dimensional motion, some molecules are moving horizontal, x-axis, some on the vertical, some on the z-axis, which is perpendicular to both x and y. Now, if this number is distributed evenly among the axes, so each molecule, each axis is carrying the same number of the molecule. So the total number of the molecules which are moving in this direction, mean along the x-axis, is n by 3. So the total force which is exerted at the one wall along the x-axis will be 1 by 3n times mv square over L. And it can be written as Fx is equal to 1 by 3 nm over L. But do remember this speed, it is the speed of the all molecules. Now, here, the temperature of the gas is little higher than the gas at the bottom. So the speed at the bottom is less, and the speed of the molecule at the bottom is large. So due to difference in the speed from bottom to the top, we can take here the average speed. Now, this is the force which is exerted at one wall horizontally, mean collision at this wall. If area of this wall, length into width, is calculated, and then force is divided by area, we can calculate the pressure. So the pressure exerted along x-axis at this wall, force along the x-axis divided by area. So the pressure along the x-axis, force is 1 by 3 nm c square. Instead of V, we can write C divided by length and whole divided by area, which is L square. Now further, this pressure along the x-axis, it becomes 1 by 3 nm, this C square average divided by L square and L, it becomes L cube. So the pressure along the x-axis, it becomes 1 by 3 nm, this C square average over L cube, mean volume of the gas. Okay, number one, according to the Pascal rule, fluids exert pressure equally in all direction from the Untitled chapter pressure. So the force exerted at this wall of the container, exactly here, exactly here, exactly at the front, exactly at the bottom. So this formula is the actual pressure of the gas. So the pressure exerted by the gas is 1 by 3 nm over V into C square average. But this C square average is known as mean square speed, not the average speed, because almost 71% of number of the molecules of the ideal gas are moving with this speed. So it is named as mean square speed, not the average speed, okay? When square is cancelled by taking the under root, and this speed is called then root mean square speed, R for root, M mean square and speed. So root mean square speed. So this is the speed which is actually kept by the 71% of the molecules in the gas. So that's why it's not called the average speed. It is called root mean square speed. With square, it is called mean square speed of molecules. Okay, so this is the pressure of the gas now, because gas exerts pressure equally in all direction. So one side pressure is exactly the other side. So this is the total pressure, O-level pressure chapter. Now from this, we can write 1 by 3 Nm over volume. Now mean square speed. This m is the mass of one molecule. Nm is the total mass of the gas. So this is the total mass divided by total volume of the gas. So we can write 1 by 3 density of the gas into mean square. So Nm over V is the density. So this mean square speed can be written as 3 times pressure over density, and the under root of both sides, 3 times pressure over density under root, mean square speed under root. So it becomes root mean square speed. It is 3 times pressure over density. And do remember, due to formula, pressure is equal to rho gh. Pressure and rho density both are directly proportional. If this density becomes double, pressure also becomes double. So there is no effect on the speed. It means VRMS or root or mean square speed both don't depend on pressure and density of the gas. So this root mean square speed does not depend on the pressure and density, because when the pressure becomes double, the density becomes double. So it is only calculated by these two. Okay. Now this VRMS is called root mean square speed. S stands for square, M for mean, R for root, and V the symbol for the speed. Now suppose we have 3 speeds, 200 meter per second, then 220 meter per second, and then 240 meter per second. If the question is calculate average speed, then the simple math, 200 plus 220 plus 240 divided by 3. So the answer will be 220 meter per second. But if the question is calculate VRMS, then this S stands for the square. So we will take the square of all 3. And then M stands for the mean. So we will take the mean of these 3. And the R stands for the root. And then we will take the under root. So this answer will be the VRMS speed. This is the method to calculate the average speed and the RMS speed. So this is the difference. Now, according to Maxwell distribution, this is the number of the molecules of the gas and this is the speed. So the majority of the molecules are having this VRMS. So this speed is VRMS, and this is called RMS, speed VRMS. So according to Maxwell-Boltzmann distribution, right? Now, the formula is 1 by 3 Nm over V into mean square speed. We have done this, we have derived this. So it can be written as pressure into volume 1 by 3 Nm mean square speed. Now this is the formula for the ideal gas, but we have done that the ideal gas obeys all gas laws, which are PV is equal to nRT. So this is ideal gas equation. This is also ideal. So we can replace this PV with nRT. So nRT is equal to 1 by 3 Nm mean square speed. Now 3 nRT divided by n is equal to m mean square speed. Okay, so n is the number of the moles and the capital N is the number of molecules, and we have done that n is number of moles multiplied by Avogadro's constant. So m mean square speed. So small n cancelled. So this is 3 times capital R is the molar gas constant. And this is Avogadro's constant into temperature is mc square, mean m into mean square speed. To derive kinetic energy equation, we will multiply both sides by 1 by 2. So 1 by 2 mean square speed is equal to 1 by 2, 3 mean 3 by 2 R over NA into T. Now look, R is molar gas constant, Na Avogadro's constant, and the ratio of these two, division of these two is called Boltzmann constant. So this K is Boltzmann constant. So instead of R over Na, we can write this. So first 1 by 2 m mean square speed 3 by 2 kT, where K is this. Now, this is the kinetic energy of one molecule, but this energy is the average kinetic energy due to this speed, and this mass is just one molecule. So this is the average kinetic energy of the one molecule in the gas, ideal gas. It is 3 by 2 kT. Now for the total kinetic energy of the whole ideal gas, so kinetic energy total, this is the energy for one molecule. So we will multiply it by the number of molecules, which is capital N. So the total kinetic energy average of the ideal gas is then 3 by 2 nkt. So do remember, the 3 by 2 kT is the average kinetic energy of the one molecule, and 3 by 2 nkt is the total average kinetic energy of the molecule. Total kinetic energy of the ideal gas. Look, in ideal gas, the total energy is approximately equal to its kinetic energy because the potential energy negligible we have done in last lecture. So the total energy, which is E or sometimes U, it is 3 by 2 nkt. So kinetic energy total of the ideal gas will be considered its internal energy, its total energy of the molecules. Now come back to this equation, which is 1 by 2 m mean square speed 3 by 2 kT. identify the constant. This is constant, this is constant, this is constant, this is constant. So this mean squared speed directly proportional to temperature, but in Kelvin. So mean squared speed does not depend on the pressure, does not depend on the density. It depends on the temperature of the gas in Kelvin. So we can write then mean squared speed 1, mean squared speed second, and this ratio is T1 over T2, but this must be in Kelvin. So the kinetic energy of the gas depends on the temperature in the Kelvin. Both are directly proportional. So thermodynamic temperature scale and kinetic energy average of the molecule, both are directly proportional. Mean average kinetic energy directly proportional to temperature in Kelvin, not in Celsius. Okay, if the square is cancelled, then the under root both side. So T1 over T2 is equal to mean square speed 1 over mean square speed 2 under root. Then it becomes RMS speed 1 divided by RMS speed 2 is equal to T1 over T2 under root. So mean square speed directly proportional to temperature, but RMS speed directly proportional to temperature under root. Right. If this is the Maxwell distribution graph, this is speed here, meter per second, and this is the number of the molecule. If this is the graph, and if this is considered the maximum number of the molecule, so this speed is called most probable speed, the maximum. And then this speed, which is smaller than the 100%, is called the average speed. But the RMS speed is carried by almost 70%. If this level is the 100%, then 71% level will be this. So this speed will be RMS speed. So RMS speed is actually the carried by more than 70% of the molecule. If we have to label the speed, so the majority, the maximum, VP, then less than that, V average, and this, VRMS. So it means RMS speed is greater than the average speed, and the average speed is greater than the most probable speed. Mean the most probable speed is smaller than the RMS speed. So RMS speed is greater than the average speed, and the average speed is the most probable speed of the molecules. So this is further explanation of the Maxwell distribution. Okay, next, in gases, molecules are moving randomly. But before two collisions, it is considered that the speed velocity of the molecule is constant, and after the collision, it changes its direction and the speed. So when air molecules are examined under powerful microscope, then this is the behavior of the gas molecules between two collisions. This is number 1, this is number 2, number 3, number 4, number 5, number 6, number 7 collision. Between two collision, the direction and the speed of the molecule remain same, and this is examined by by a scientist which is called Robert Brown, and it is known as Bronian motion. So when powerful microscope is used to examine the behavior of the molecules, right, and the gas, so this is actually the motion. So according to the Robert Brown, smoke particles were used to make gas molecules visible, because the gas air molecules are not visible, but when they collide with the smoke particles are greater in size but smaller in mass as compared to the air molecule. When the light is focused on the smoke particle, they will appear like a bright speck. So these smoke particles, after the reflection of light, will appear as a bright speck. So these are actually the bright specks which are moving, right, from one collision to the other, right, from 2 to 3, 3 to 4. And this is actually the behavior of the gas molecules, because the gas molecules are making them, right, move in this pattern. The gas molecules are colliding with the smoke particles. Smoke particles are visible. So the behavior of the smoke particle is actually the behavior of the gas molecules. And this is called Brownian motion. Okay, suppose this is the glass container and it contains the mixture of gas and smoke. When the high intensity light is focused on these particles, smoke particles will appear like a bright speck, and when they are viewed by a powerful microscope, this is the microscope, so they will show behavior like this. This is Brownian motion, and it is the behavior of the gases, right, due to their random distribution.